Good morning, everyone. Welcome to this class for Math 2421 probability course this semester. My name is Ke Wang. I'm an associate professor in the math department. So you can, my office is in room 3434, and you can reach me by email. That's preferred. You send me email at this email address. So I'm teaching two sections, or both sections for Math 2421 this semester. This section is L2, and we meet on Monday and Wednesdays from 9 to 10:20 a.m. each week. So this is one of the least favorite lecture times. Also, I don't really enjoy teaching in the very early morning, but I hope that doesn't prevent us from performing well in this course. So this section is split into two tutorial classes. We have two TAs, Liu Yuyao and Zhang Zihao, teaching these tutorial classes. In the tutorials, basically, we'll go over some actual problems related to the course materials. And if you have any question, you can also get in contact with them. So this course is a very beginning course for probability theory. But I know that this is a prerequisite for many other courses that are going to take. So, and also I would say it's a very important course, more and more important nowadays. So regarding the textbook, we don't have a fixed textbook. So actually I have uploaded a PDF file on Canvas already. If you are interested, you can, in these textbooks, you can take a look. So the lecture notes is based on this book by Ross. He has a probability book for undergraduate students. If you are interested, I can also send you the details. But it doesn't really matter if you have the textbook or not. For the assessment, we have one midterm exam and one final exam. The midterm exam will be in class, so it's 18 minutes. So the midterm exam will be on March the 18th. Please mark your calendar. So it's in the morning from 9 to 10:20 during the lecture time, but we will probably find another classroom. So as the date approaches, I will upload the seating plans, so you'll see where you are going for taking the midterm exam. And the final exam will be arranged by the ARO. So I don't know the detail yet, but the time for the duration for final exam is 2 hours. And also we have homework assignments. So we have 5 homework assignments in total, and these homework assignments are up. You can find them on Canvas. I will go over it a little bit later. So we have another thing called the attendance check. So we only have 3 random attendance checks through the semester. So I will drop the lowest. So it's, this means that if you are present for your attendance check, you get the whole, the total point 2 points. If you are here for the 2 or 3 checks, if you are only present for 1 check, you get 1 point, and you are not here at all, then you get 0 point. And I will not give advance notice when these checks will occur. Of course, that's against the purpose for random attendance. And also, there's no makeups for any reason, including illness, because I dropped the lowest. And in case you have long-term disabilities that prevent you from coming to classes, you should contact me in advance. We can discuss the alternatives for this part of the points. So the purpose of attendance is to award students who come to classes. So that's a percentage for how we give grades here. Homework exams takes 15 points, 15%. So basically 3 points for each assignment. Class attendance 2 points. Midterm exam is 33 points. Final exam is 50 points. Okay, let me go to the Canvas. So this is a Canvas set for our section. The syllabus overall is uploaded in the course information. And you can find the textbook PDF over there. It's basically identical to our lecture notes. So I usually upload the clean slides before the lectures, so you can download them and take a look in advance. And after each lecture, I will update the filled in the lecture notes to this part. So if you don't want to take notes, it's okay. You can just download from there. And usually I will provide the lecture recordings. And I will upload some past papers and information for the exams before midterm or final exam in this module. And you can find actual practice problems here if you want to do more exercises. I didn't provide a lot of actual questions. You can feel free to find them online or even ask the AI tool to generate more questions for you. Nowadays, it's very convenient for the learning process. And tutorial notes will be uploaded in these modules. And the homework, you can find them in this assignment part. So we have 5 assignments. So the first one will be open at noon today. For each assignment, you have like around 3 weeks to finish them. And there are like not ton of questions, like 10 or 15, something like that questions. So I believe that's sufficient time for you to finish each assignment. So this means that once an assignment is closed, it will never open again. So I don't recommend to finish it right before the due day, because you may encounter some technical questions, and that's not my responsibility. I will not reopen it due to you finishing it at the last minute, okay? Because I used to do that once, but I made some mistake and screwed other people's points. I don't want that mistake to happen again, so I don't want to risk this. So I will not do that anymore. So another thing is about the question and answer part. I think I have sent you an invitation link to join an online platform called Add Discussion. So I would go over that a little bit next time during lecture. Based on my past experience, I usually, if I communicate with students by answering questions by email, that's very efficient, because sometimes I need to answer the same question over and over again, like 10 times something. So nowadays, I'm moving all the questions regarding like how to do this question and some minor question about the midterm, lectures. All these will go to the online platform. So I will usually take a look at the platform each evening before I go to bed. So I answer the questions at that time. I will also ask our TAs to go on the online platform to answer the questions. So usually you will get very prompt replies if you post your questions on the online platform. Another advantage is that other students can see your answer. So I suggest to put proper labels on it. For example, you are welcome to ask questions from assignments. So you can put your title, assignment 1, number 10, or something like that. So in case other students have the same question, you can just click in and see the answers. And of course, if you have other questions, like personal questions, if you have something you want to discuss more privately, you can send me emails. And you can also ask private questions on the platform. So I will go over that a little bit next time. So I think that's all I want to say for now. Any question regarding the course? Okay, if not, let's go to the course materials. So we'll aim to go through 8 chapters for this course. Let's start with a few words. What is probability? So probability is simply how likely something happens. For example, if a coin flipped, it randomly flipped, how likely it lands on head or tail. And initially, probability theory is a bunch of questions raised by gamblers when they want to compute their odds in various gambling games. Nowadays, it's becoming a rigorous and fundamental mathematical tools important for many other disciplines. So why should we learn probability? Just a few words here. Nowadays, randomness become prevalent in real life. For example, you are interested in the revenue Apple stores at 8 p.m. next month. You can view this as a random number. And the length a patient with cancer can survive. This is also a random number. And also you can interested in like how likely you can win a lottery, what is the chance we have rain tomorrow. These are all random. And probability has been a fundamental tool for modeling, analyzing randomness. So for example, you can also try to analyze what is the most likely revenue of Apple Store at 8 p.m. next month, what's the likely length a patient with cancer can survive. You can analyze this kind of question. Third thing, probability is fundamental tool for statistics, machine learning, and also artificial intelligence nowadays. Especially, we have this era of big data. We have tons of data generated every day. Randomness helps to set up the correct models to accelerate the computation and do the analysis. So just a few words on this. So in this course, we will explore the mathematics behind the randomness and certainty and quantification of probabilities. So I hope after this course, you will be able to develop the fundamental tools and the knowledge needed to understand and work with probability in your chosen majors and other fields. And we will start with chapter 1. So actually, the first 3 or 4 chapters for this course are relatively straightforward, especially the first 2 chapters. The first chapter is about counting things. This is something you are familiar with from high school. We'll probably, in this chapter, we'll probably focus on using combinatorial techniques to compute the probabilities. So this is how we compute probability in the very beginning of this probability theory. We only consider finite things now. And many of these concepts you should be very familiar from high school, at least, or even earlier. So anyway, through these concrete probability computations, they will help us to build an intuitive understanding of the probability theory. So later on, as we progress in the course, the material will become more and more abstract. And we also incorporate more advanced tools like calculus and linear algebra. It will get harder and harder. But for the first few chapters, in my past experience, most students find them pretty easy, actually. So in the first few chapters, I will go in a faster speed because the difficulty level is very low. So anyway, let's start. So let's use some simple examples to get started. For example, if we randomly pick up a ball in a given box, 9 balls in them with different colors, then what is the chance of selecting a red ball? So this chance is the probability we are talking about. So the solution is that we see there are 9 balls in the box, and 4 of them are red. So intuitively, we know the chance of selecting a red ball is 4 over 9. So it's computed as 4 outcomes are red. We count how many red balls are 4, labeled with 3, 4, 7, 9, and count the total possible outcomes. The total number of balls 9. So from this very simple example, we can summarize how we can use counting to compute probability. So this will be just a quotient. This probability is number of outcomes you are interested about then we count the number of total possible outcomes, and their quotient is the probability we are talking about. Okay, so that's how we are going to compute the probability in this first 1 or 2 chapters. So that's why we want to learn something about or renew something about counting. So let's see another example, slightly more complicated. Here, let's think about now if we randomly pick 2 balls simultaneously in this following box, which contains 5 balls with different colors, different labels, what is the chance that the 2 select balls are both red? Okay, so you can try a little bit, and if you want to use the previous generalization to compute this probability, we find out the total number, the number of total possible outcomes, and then find the number of outcomes you are interested. So one sort of naive way of doing that is you list all the possible outcomes and identify rows you are interested about and find those numbers and divide them. So you can list all possible outcomes for the ball you select is 1, 2. Maybe I shouldn't write it this way because I should write in the brackets because we don't count the order. 2, maybe I list this 1, 2, 1, 3, 1, 4, 1, 5. Then we have 2, 3, 2, 4, 2, 5. Then 3, 4, 3, 5. Then 4, 5. Okay, so I'm taking 2 balls simultaneously. So you cannot take like two balls with both numbers 2. So you can see the total number is 10. Then identify rows we are interested about. We are interested in both select balls are red, so there only occurs when you have select 2 and 4. So there are only one number for the number of outcome you are interested about. So this probability is 1/10. Okay. Okay, so after we introduce some more advanced tools, you can find a more convenient method to solve this problem. Let's see another more complicated examples. So here we have a communication system which consists of n identical antennas lined up in linear order. So you can think of lined up in a line. The system can receive signals as long as no two consecutive antennas are defective. So in other words, if you have two defective antennas next to each other, this system is not working. So if it turns that exactly m of the n antennas are defective, what is the probability that the system can receive signals? Here are some figures for a working antenna. Working system is we don't have any two consecutive antennas defective, and otherwise in the second configuration we have two defective antennas next to each other. It's not receiving signals. That's a bad system. So we want to find a chance that the system can receive signals. Okay, so this example may seem a bit hard at first sight right now. And let's look at a simplified version of it. So we look at the case that n equals 4 and m equals 2 and solve it. So later on, we'll come back to this example and using different ways to provide a solution. So let's look at the simple one. If we just look at the special case, we have like 4 identical antennas lined up. M equals 2, 2 of them are defective, and let's find the chance that the system can receive signals. So we'll still use the previous way. We find the number of total possible outcomes and find out the number of outcomes we are interested about and divide these two numbers. So to make things easier here, I'm going to use 1 to represent antennas that is working, and 0 is that it's defective. And we line up the zeros and the ones. And also, it's that these antennas are identical, so we cannot distinguish the ones and zeros here. So let's arrange these 2 zeros, 2 ones in a line. So you just draw all these configurations. You can have 0, 1, 1, 0, and all these. You can see there are 6 possible outcomes in total. So total number. This equals 6. And then you identify rows you are interested about. So we want to find the probability that the system can receive signals. So we want to find out those line-ups that we don't have the 2 zeros next to each other. So you can see only this these 3 are working. So these 3 working systems. So for this question, specific questions, the probably we want to find out is 3 over 6 is 1/2. Okay, so right now we didn't use anything of the ones to solve this kind of question. You can even teach like primary students to solve this problem if we can count. So what we did is that now the probability the system works is we count number configurations that the system works well and divide total number of possible configurations. And so this example just shows that this counting is important in solve some kinds of probability problems. So we want to have some useful methods, more effective methods for counting the number of ways that things can occur. And the mathematical theory of counting is formally known as combinatorial analysis, or simply combinatorics. That's another area of mathematics. So we'll start with the very basic one. It's called the principle of counting. Here in this course, we're going to use this notation called experiment, or sometimes we say it's a random experiment. This concept denotes a process that the outcome is random. So we'll perform random experiments and compute probability of things we are interested about. Example of the experiment is like you randomly pick a number from a set of given numbers and randomly toss a coin, randomly roll a die. These are called experiments. Okay, so the first theorem is called the basic principle of counting. So it says, suppose that there are 2 experiments to be performed. Then if experiment 1 can result in any one of m possible outcomes, in this, put it in the box. And if for each outcome experiment 1, so if you have in experiment 1 you get this random this outcome 5 occurs, then you look at the possible outcomes for experiment 2. There are n possible outcomes for each given outcome in experiment 1. Then in total, there will be m times n possible outcomes of the 2 experiments. Okay. So we call this basic principle of counting. Even though it looks very simple, we can deduce more advanced counting methods from this principle. So provide a little bit of proof. So suppose there are the 2 experiments to be performed, and if experiment 1 can result in any, I will not read again. So the proof here is we are going to list all the possible outcomes and see how many we have in the list. So we use this notation. We say the outcome, we denote one outcome is this ordered pair. We call them I and j. This means experiment 1 results in its jth position, its jth possible outcome, and experiment 2 then results in jth possible outcomes. Okay. So if you have 1, 2, this means experiment 1 has outcome 1, experiment 2 has outcome 2. And then we just list all these possible outcomes. In each row, we fix the outcome of the first experiment and list the possible outcomes of the second experiment. So in total, we have m rows. And then for each column is you fix outcome in each second experiment and count for the possible outcome in the first experiment. So we have n columns. So in total, we have n times m, just ordered pairs. So that's the total possible outcomes. And let's apply this to solve some problem examples. In a small community, we have these 10 women. Each of them has 3 children. If one woman and one of her children are to be chosen as mother and child of the year, how many different choices are possible? So you can think of this as, if you want to apply this basic principle, you can think of these 2 experiments to be performed. In the first experiment, we choose the mother of the year. So there are 10 candidates, 10 possible outcomes. So maybe a little detailed. This is for experiment 1. Choose one of the 10 women. And then for the second experiment is fix the outcome in first experiment. So if we have chosen a woman, we choose one of her children, and there are 3 outcomes for each outcome experiment 1. So 3 is for experiment 2. For a chosen woman in the first experiment, she has 3 children to be chosen from. Okay. So anyway, it's a very simple question. You get 30. And similarly, I see the second example in a class of 30 students. We choose a present and a vice president. So you can also think of that as 2 experiments. In the first one, we choose the present. There are 30 candidates to choose from. Then once you have chosen the present, you have 39 students remaining for the choice of the vice president. So multiply the outcome second experiment is 39. And of course, we can generalize this basic principle of counting. We don't just look at 2 experiments. We can have R experiments to be performed. So for example, the first one results in N1 possible outcomes. For each of these N1 possible outcomes, there are N2 possible outcomes, the second one. And for each of the possible outcomes, the first 2, there are N3 possible outcomes, the third experiment. And in total, we will have this multiply all these possible outcomes together for this R experiments. Okay, so let's apply it for the next example. How many different 7-place license plates are possible if the first 3 places for letters and the final 4 places for numbers? So we can think of this as 7 experiments to be performed. And for the possible outcomes for different experiments, different. For the first 3 places, we fill in the letters. Letters is from A to Z. There are 26 letters. And for the final 4 places, we'll fill in numbers. The numbers, you can only fill in the single-digit numbers, 1 to 9. There are 10 of them. Okay, so just apply the theorem. For the first experiment, the first place, you have 26 choices, possible outcomes. Then you multiply the outcomes for the second one, is 26. Then multiply 26. You just move on. For the first place, fill in numbers, there are 10 choices. Then multiply 10. Okay. Okay, so for the final answer, I don't really need you to compute the exact value. If you don't have a calculator, you can just simply leave the expression like that, or write this is in the powers. And it's optional to give an exact value using calculator. Okay. So last time I teach this course, in the midterm exam, I gave a similar question like this: ask how many ways we can fill in the car plates if you fill in some certain things. And there was a student whose answer gave me a very weird answer. And the student drew a circle next to that. So it took me a while to understand what he's thinking about. So maybe their English is a barrier. So I think he literally understands their license plates, car plates as a plate. So he's trying to fill in their plate with numbers. So just pay attention to the English part. It's not like it's a car plate, what you see in the cars. It's not an actual plate. Okay, let's see a more complicated one with bit constraints. How many different 7-place lesson plays are possible if the first 3 are for letters, final 4 for numbers, and repetition among letters or numbers were prohibited? So we have a little bit of constraints. In the first 3 places, still fill in letters. Last 4 will fill in numbers, but we don't want the letters or number to be repeated. Okay, so just use this basic principle counting. In the first place, you have 26 choices. Once you have a fixed outcome in the first place, you don't want the letter to be repeated. So we have 25 choices for the second place, then 24 if the first 2 letters are chosen. And for numbers, similarly, for the first place, you have 10 choices. And for the next one, you are left with 9 choices. The third one, you have 8, then you have 7. To avoid repetition, okay, so we write down the explicit number to get the feeling about how different these numbers from the first place. Okay, so let's see the next concept. The next thing is about permutations. So you can think of this question, how many different ordered arrangements? So the key part is we consider ordered arrangements. And in this example, we consider 3 letters, A, B, C, are possible. By direct enumeration, we can see there are 6. You can list all of them, A, B, C, A, C, B, and G's. Each arrangement is known as a permutation. So a permutation just refers the arrangements or ordering of the set of objects or elements. So in a permutation, the order of the elements really matters. Okay, so let's see how we can deduce the permutation number, the number of permutations from the principal counting. So in this simple example, let's going to have 3 objects. There are 6 possible outcomes. I'm explained by basic principle. So you can think of filling the 3 places by the given 3 letters. In the first place, you have 3 possible outcomes to choose from. So you have 3. You can think of 3 experiments. So the first one, you have 3 possible outcomes. For the second one, if you fix the first position as a letter, you are left with 2 letters to choose from. So you multiply 2. For the second experiment, for the last one, you have only 1 left. So the answer is 3 times 2 times 1. And then, of course, we can generalize this to if you are given n distinct objects, the total number of different arrangements. This is called the number of different permutations can be deduced in a similar way. We consider n experiments. So we can think of filling this n boxes with these given numbers. You can think of n numbers, n letters, they are distinct. So to fill in the first position, you have n choices. For the second position, there will be n minus 1 choices. And third one, you have n minus 2 choices. And then eventually, for the last one, you have only 1 left, have n, 1 choice. So multiply together, you get this number is n times n minus 1 times n minus 2. Then just multiply together. And for convenience, we are just going to use a notation. This reads as n factorial for this. This is a number of arranging n distinct objects in line. And also, we have a convention that 0 factorial is denoted as 1. And also, you can compute like 3 factorial is 3 times 2 times 1 equals 6. 4 factorial is 4 times 3 times 2 times 1. And you can see this is 4 times 3 factorials. This is 4 times 6, 24. 5 factorial is 5 times 4 times up to 1. And then you can see recursive relationships is 5 times 4 factorial equals 120. So in general, we can have this n factorial equals n times n minus 1 factorial. Okay, so this is a useful recursive relationship about the factorials. Okay, let's see some examples. So it's simply just n factorial. Okay, so here example is sitting arrangement in a row. So 9 people sitting in a row. So yeah, arranging and 9 distinct people in a line. The order matters. So in total, it's 9 factorial equals 362,880 ways. Okay, straightforward application. Let's see another example. Let's arrange 5 balls in a row. 2 of the 5 balls are red. So assume these red balls are alike or indistinguishable. And 3 of them are blue. So these blue balls are alike. Let's see how many different ways we can have. And if they are all distinct, we have just simply 5 factorial ways. Arranging them. But some of them are alike, red balls are alike, blue balls are alike. So we have overcounted. So what we do is that we just fix a configuration and count how many times we have overcounted. So then we use 5 factorial to divide how many times we have overcounted. So let's fix a configuration and see how many ways we have overcounted using waving them as all distinct. So for example, we have you have 2 red balls, red, red, arranged together, and blue, 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 like this. And if you treat them as all distinct, the red balls and blue balls distinct. And for this configuration, we actually count the order occurs between the 2 red balls. We view them as R1, R2, so we can have R1, R2, R2, R1. So there are 2 factorial ways if you count them as distinct. So this pair is counted 2 factorial times. And similarly, for this triple, the 3 blue balls, we also view them as distinct. We counted previously. We view as them B1, B2, B3. So we count them as arranging 3 distinct objects. So that's 3 factorial ways. So in total, this configuration is counted 2 factorial times 3 factorial times. Okay. So to get the correct number, we are going to use 5 factorial to divide this overcounting number. 5 factorial divide 2 factorial, 3 factorial possible ways. Okay, so this is arranging things with a little bit constraint. And let's generalize into a more general discipline. You can apply this formula directly. So we are arranging 5 balls in a row in the example, some of them alike. So you can think of, now you have n objects, of which n1 are alike, n2 are alike, and r alike. Then in total, there will be n factorial divide the permutation occurred among these alike objects. So it's n factorial divide n1 factorial n2 times n2 factorial times up to nr factorial, which is different ways for. Okay, so the proof exactly how we work out the previous simple example. Okay, let's see an application of this result. How many ways to rearrange this word Mississippi? So let's count how many. We can apply the previous theorem. We are arranging n objects. So now n is the number of letters in this word. So we arrange n equals, you can count, these are 11 letters. And actually, there are only 4 distinct letters, M, I, S, P. And for each letter, N1 is the number it appears in this word. So there are only 1 M. For I, there are N2 equals 4 of them. For S, that's N3 is the number of S appear in the word. And P, there be N4 equals 2. So you can think of this arranging the 11 letters with N1 M's, N2 I's, and 3 S, and 4 P's. These are like objects. So the formula you can apply directly is n factorial over n1 factorial, n2 factorial, and 3 factorial, and 4 factorial. Just multiply together. So just plug in. Okay. And if you want, you can simplify this number. 34,650. Let's see, answer. Okay, let's see some other counting with permutations with a little bit other constraints. So let's think about this together. So it's about sitting in a circle problem. There are 10 people sitting around the dining table. And now it's the relative position that really matters. Who sits next to whom? Who's on the left? Who's on the right? Let's find out the number of sitting arrangements. Now we have a little bit of symmetry coming in. Okay, so let's maybe look at this together. So here we have this short-up rotation invariance. If we just arrange them in order, we have n factorial ways to arrange 10 people sort of in a line. But now you are sitting around a round table. It doesn't matter if you rotate them. If these 10 people have sitting in the table already, and you like them to shift it by 1 position on the right, each of them, you get the same sitting arrangement. So this means that we have this rotation invariance. And you can solve this problem by thinking for each sitting arrangements, how many times you have overcounted if you view them as sitting in a line. So let's fix the sitting arrangement and see how many times we can swap the sitting so we have the same sitting arrangement. Okay. So you can definitely shift each one on the right, maybe clockwise by one position, the same. You can maybe just look at just one people, one shift to the previous two position, then it's the same, then shift to the previous three, then shift it around here. So you can, this one can take any of the 10 positions with other people moving together. So we have this, for this configuration, these 10 sitting arrangements are the same. So for each configuration, we have overcounted 10 times if you view they are sitting in a line. So in total, we have 10 factorial over 10 equals 9 factorial ways of arranging them in the round table. And more generally, if you have n people sitting in a circle, then the number is n factorial over n. So n factorial, we said, is n times n minus 1 factorial. So this simply might be n minus 1 factorial possible arrangements using the same argument. Okay, let's see another variant of this arranging things with another bit of symmetry. So let's also consider this example of making necklace. Now we have n different pearls stringing in a necklace, and we want to find the number of ways stringing the pearls. So just maybe start to think about it. So we have different kinds of symmetry coming in. Okay, so the answer is that first, this is sitting in a round table kind of problem. You can have like n minus 1 factorial arrangements. And let's think of if we have our content here. So actually for a necklace, it's different because you can, for a necklace, you can flip it by looking at the mirror. These two configurations are considered the same necklace. So you have this reflection symmetry here. So for a fixed configuration in this sitting in the round table, if you flip it, then you get equivalent necklace. So for each configuration, we have overcounted twice. So the final answer is n minus 1 factorial over 2. Okay. So in this counting, we need to pay attention to different symmetries in their more complicated situations. Okay, so this is about the permutations. Let's look at another concept called combinations. So this kind of concept comes from example like this. How many ways can we choose 3 items simultaneously from a set here given is 5 objects, A, B, C, D, E? Okay, let's find out this number by using direct counting. You can use the previous implementation or basic principle counting. So first, we have 5 ways to choose the first item, 4 ways to choose the second, 3 ways to choose the third. So the number of ways of ordering 3 items chosen from the A, B, C, D, E is 5 times 4 times 3. So it gets 3 ordered triples. However, here, the order for each configuration does not really matter because ABC, ACB, BCAC, these are considered the same group. So for fixed configuration ABC, these three factorial arrangements of it actually account for the same thing in these three atoms we've chosen. So to define the answer is 5 times 4 times 3. The y, the permutation that occurred for each configuration, is 3 factorial. So here for each group, the order is not important. So combination is different from permutation, is that we don't really count in the order now. So basically in combinations, we don't care about the order of the atoms are chosen or arranged. So do not care about the order. So you sort of divide 3 factorials, the ordering of the 3 atoms in the denominator to erase the ordering occurred among them. So let's generalize the previous example into this theorem. Generally, if there are n distinct objects of which we choose a group of R atoms, the number of possible ways is exactly the same computation. So if you think of first, if you have the ordering among the R atoms, you can use the permutation of the basic principal counting. You have n times n minus 1 times n minus 2 times n minus R plus 1. So in numerator, you have the product of R atoms, R terms. Now the ordering does not matter. So for each fixed configuration, you can permute the ordering, permute the items to create n factorial, same thing. So divide n factorial to erase the ordering of them. Okay, so let's rewrite this expression as something we're more familiar with. So first we want to write everything in terms of factorial, because in the numerator it's a truncated factorial. It's n times n minus 1 each time it reduced by 1, and then you just stop at, if you have a product of R atoms, so you stop at n minus R plus 1. But if you continue to multiply this minus 1s, n minus R, up to 3 times 2 times 1, you get n factorial. So this is neat. So we keep the n factorial, but we should multiply the same added expression in the numerator, which is n minus R times n minus R minus 1 times 3 times 2 times 1. And this is also a factorial. It's n minus 1 R factorial. So this expression can be written in a shorter way, n factorial over R factorial times n minus R factorial. And then I think you probably have introduced this notation in high school. You can either write this expression as n, small n, the big C, standing for choose R, or actually in more standard notation where I write in this way, with a big bracket, n is in top, R is in the bottom. It's also written as n choose R. So you can use whatever way you are used to. I'm used to the second way. So it's the same thing. So I don't know. I never wrote this way in big CR. But if you're comfortable with that, it's totally fine. So anyway, there are same expression representing this expression n factorial over R factorial times n minus R factorial. Sometimes if this R is small, it's actually easier to compute it as the original definition. In the top, you have the multiple of R atoms starting from n, each time reduce 1. Denominator have R factorial. And this is called their number combinations. So this represents this number. You choose a group R items from n distinct objects. The number is n choose R. We use it directly. And about this number, let's introduce some properties to facilitate our computations. So the first property is n choose R is equal to n choose R minus n minus R. That's the first property. Here R is equal to 0, 1, 2, and n. Okay, so let me write down a short proof. Maybe just mention the proof. There are two proofs. The first one is algebraic. You just check both sides are the same. Using their definition of n choose R, just plug in, you see the same expression. And the method 2 is sort of combinatorial. So n choose R, you can think of this as you are choosing R balls out of n distinct balls. So the remaining balls are n minus R balls. So you can sort of think of, if you choose R out of the n balls, the remaining balls is the same as you choose n minus R balls out of the n balls. Okay, so maybe I write in a more general way that's used for later generalization. The second method, we can interpret so these numbers are called binomial coefficients. So we'll see that immediately. So n choose R are all binomial coefficients. So we can interpret this binomial coefficient like n choose R as we are dividing n distinct objects into two groups. With sizes R and n minus R respectively. So this is a useful way of understanding binomial coefficient. So n choose n minus R with the same interpretation is dividing n distinct objects into two groups with sizes n minus R and R respectively. So they are the same. And later on, we'll introduce some numbers similar to binomial coefficient as dividing n distinct objects into like 5 groups or 4, 10 groups with different sizes. Some other conventions that n choose 0 is the same as n choose n, so by the same. And you can compute this is equals 1, or just you choose 0 object from the n balls. There's only one way to do that. And also some convention, if the R is negative or R is bigger than n, so we denote n choose R as 0. So basically you cannot take 5 balls out of 3 balls. That's not possible. Okay, so let's see some examples related to this binomial coefficients. In the example, a committee of 3 is to be formed from a group of 20 people. First question, how many possible committees can be formed? So this is straightforward. We choose a group of 3 out of 20 distinct objects. So the number is simply 20, choose 3. And if you want to simplify it, just 20 times 19 times 18 over 3 factorial, which is 6. Just compute it by hand. The second question is, suppose further that 2 guys, Peter and Paul, refuse to serve in the same committee. How many different possible committees can be formed with the restriction that these 2 guys don't serve together? Okay, so for this counting problem, usually you have different ways of doing so. So here, let me present 2 ways. You can choose different other ways, whatever you find more comfortable for yourself. So if you don't have the constraint, we can just have the answer is same as the first question, 20 choose 3. Then we are going to remove those committees that with Peter and Paul in this committee. So we just subtract the numbers we don't want, which is what occurs if this given situation occurs. Peter and Paul both serve in the committee. So if you are already in the committee, we just need to choose the 3rd people from the remaining 18 choices. So we are going to subtract the number of committees with Peter and Paul both in. Okay, then that's the answer. So it's the previous number, 1,130 minus 18. Get this. The second method, you can count case by case. So we just count directly, but we split into 2 cases. The first case, we just count the number of committees that with this this restriction. So the first case is in this committee, none of them is in the committee. None of Peter and Paul. Okay. So we just choose 3 members from the 18 people. We don't consider Peter Paul. So it's 18 choose 3. So this is our number for case 1. Case 2 is one of them is in the committee. Just one of them. So we choose either Peter or Paul. We choose one from them. So it's 2 choose 1. And then times the number possible we choose other members. So we have 18 candidates. We choose 2 of them. So in total, just sum up these 2 cases. That's the only cases we have. We should have the same number. Okay, let's continue and let's go back to this example we mentioned in the beginning about arranging the antennas. Now let's provide one way to solve it. In this example, let's consider a set of n antennas, of which m are defective and n minus m are functional. Assume that all of the defectives and all of the functionals are considered indistinguishable. How many linear orderings are there in which no two defectives are consecutive? So we want to find the other linear ordering, arranging these antennas in a line such that no two defective ones are next to each other. Okay, so you need to find a good way to arrange these functional or defective ones. So if this looks too abstract in the beginning with this n and m's, you can always start with a small concrete example. For example, let's consider some small examples so we can be more hands-on. So assume like we have like 5 functional ones, 5 equals n minus m functional ones. And let's use a circle to represent a functional antenna. And we have 3 defective ones. Let me use a box with a cross to represent a defective antennas. So we don't want the defective ones to next to each other. So in other words, these 3 defective ones are separated by the functional ones. So for any 2 of them, there must be at least 1 functional antennas in between. So one way to solve this question is that we are going to first arrange the functional ones in a line. So we have 5 functional ones. And in order for them to separate the defective ones, so we can only put the defective ones in the slots we have created. So if we just put the defective ones in the slots, they must be separated by the functional antennas. Okay. So we have 5 functional antennas, and we'll create here 6 equals n minus m plus 1 slots to place these defective ones. For example, you put 3 here. Okay, this is a working system because they must be separated by the functional ones. So this is how we're going to solve it. So this means that we just need to find out where we are going to place the defective ones, how we place the defective ones in the 6 slots. So the answer is because the functional defective ones are alike. So the answer is how many ways you can choose the 3 slots out of 6 slots. So for this one is 6 choose 3. Okay. So in general, you can solve this question in the same way. Here, let me use the circle to be the functional antennas. These are alike. There are n minus m of them. And this crossed boxes to be the defective ones. These are all alike. There are m of them. Okay. So the first step, I'm going to arrange the functional antennas in a line. there is only one way because they are alike. Okay, so once you have this n minus m antennas lined up, we are going to look at the slots we created. So we will create, similar to the example, it's n minus m plus 1 slots. So here, n minus m plus 1 slots. And second, we are going to place the m defective antennas into the slots. In there, now we have n minus m plus 1 slots. Okay, so basically, also these defective ones are alike. So we don't really care about which one is in which slots. So we just need to choose m slots to place the m defective antennas. So the number of ways is choose n minus m plus 1, choose m. So again, draw some examples placing the defective antennas. You will see that if you put in the slots, you'll create a working system. So this is just one way of solving this kind of problem. And next time we'll introduce another way of solving this example. It depends on how you view the problem, how you arrange them, so you meet the restriction. So you can also just first place the defective ones and then arrange the functional ones in some way with some restriction. So I think for today, I'm going to just stop here, and we'll continue the theorem next time. Okay.